Okay, so I kind of have made an executive decision based on the fact that this week is kind of goofed up. Um, I'm gone tomorrow, snow day, etc. I think we're only going to do the partial fractions using the non-repeating linear factors. I'm not going to worry about teaching you um, the other two methods, so we have to keep that quiet. Although we are getting ready to post this on the internet for the whole world to see, so hopefully no one's going to see that. But yeah, I think we're just going to do repeating linear factors. So, which means you essentially are going to be able to use the shortcut to do the partial fraction decomposition. What I'm going to do for you today is just show you kind of an extension of what we did yesterday, or what I did in that last video, and actually just do a few problems where we actually find antiderivatives. You'll find that this is pretty easy. As far as the antiderivative of cosine squared, cosine to the fourth, third period, this is for you. We end up working that out in fourth period, or period 4-5. So that actually, you can look in the live stream videos on my YouTube channel. You can find that. I'll also show you how to do it on Monday when I get back. So partial fractions, non-repeating linear factors. So let's just start with a problem here. Let's say this is 2x plus 2 over x plus 1 times x minus 1. Okay? Dx. So we're finding this antiderivative. So the first thing that we're going to do is we're going to break that integrand. We're going to rewrite the integrand into a partial fraction decomposition. All right? And now we got to figure out what a and b are. So if we want to use the cover-up method, so I'm going to figure out what a is. So -1 makes that 0. Well, mitter. Okay, let's go ahead and show you what happened. I made this problem up on the spot, and something crazy happened. If I factor out a 2, I get x plus 1, right? And that's going to cancel that. So we don't even need the partial fraction decomposition. So let's start over and make up a new problem. So look for simplifying before you do the problem, always, right? Stupid. All right, here we go. Try another one. How about 3x minus 7 over x plus 1, x minus 1. That's not going to factor because I got a prime number there in the end. So try this again. We're going to break up the integrand into partial fractions. Okay. And now we'll use the cover-up method. So the shortcut, so I'm going to say -1 makes that 0. So I'm going to take -1. I'm going to plug it in for x everywhere else. So 3 times -1 is -3. Minus 7 is -10 over -1 minus 1 is -2. So that's a. And then next one, 1 makes that 0. So I'm going to cover that up. 3 times 1 is 3. Minus 7 is -4. And 1 plus 1 is 2. So 4 over 2, that's b. All right, now I'm going to go ahead and clean this up. -10 over -2 is 5. And -4 over 2 is -2. All right, and now I'm going to go back and I'm going to say, okay, now let's find the antiderivative of this. Okay, and it turns out these are both pretty easy to do. There's technically a little u substitution that you're doing here. You would say u is x plus 1 and u is x minus 1. But du is just dx, so it's a pretty easy u sub, right? So this ends up being 5 over u and -2 over, technically I shouldn't use u there, but as long as you can keep the two separate, 5 natural log of x plus 1 minus 2 natural log x minus 1. Okay, so there's the antiderivative plus chips. All right, so there's how we do a partial fraction decomposition, and then an integral on top of that. Let's do another one real quick. How about 5 over 2 minus x times x plus 3. All right, 5 over 2 minus x times x plus 3. We're finding the antiderivative here. So we're going to take the integrand, and we're going to break it up into two partial fractions. And here we go. So we're going to say, all right, let's do the cover up. So let's figure out what a is. 2 makes that 0. So I'm going to plug 2 in for x. So that's going to be 5 over 2 plus 3 is 5. So 5 over 5 is a. I'm going to just go ahead and write it as 5 over 5 for now, and then we'll go back and simplify it. And then negative 3 makes that 0, so I'll cover that up. 5 over 2 minus negative 3. 2 minus negative 3 is positive 5, so that's also 5 over 5. So basically we end up with 1 over 2 minus x plus 1 over x plus 3. And now we'll go ahead and anti-differentiate that. And you got to be careful here. And I chose this example specifically because of this right here. It's real easy when you're doing this shortcut method to get natural log happy because you always end up having a natural log. It almost always happens. The antiderivative of this term right here is negative natural log of 2 minus x. Why is that negative there? Because right here, that negative right there, when you do that u substitution, if you do it in your head, you got to remember u is 2 minus x, du is negative dx. Okay, so that's why that negative ends up being there. Plus the natural log of x plus 3. Plus chips. Just FYI, you can combine these using the properties of logarithms as the natural log of x plus 3 over 2 minus x. Because I can rewrite this as, well, let me show you the intermediate step that I skipped in my head. Natural log of x plus 3 minus natural log of 2 minus x. And then when you have two logs being subtracted, that's the same thing as the log of the quotient. Okay? Plus chips. And we're good to go. All right? So I'm going to give you some problems. I'll put them in Classroom that you can try finding some antiderivatives using non-repeating linear factors. We won't worry about the repeating linear factors and the unfactorable quadratic ones. I'm going to skip over that for now, just because we are a little bit behind, and I think it's okay if we do that. But again, just it'll be our secret. Have a great weekend. I'll see you on Monday, and that's it. Peace.